Hypergeometric distribution. Let's talk about it. When does one use a hypergeometric probability distribution? Well, we use it when there is no replacement. After all, are you really going to put that defective part back in the box, right? If you test it, you find it defective, you're not going to put it back. Okay, so if we're conducting a hypergeometric experiment, then we want to say what are the variables that we would use and what are the values that we would assign to those variables. And this, I think, is what gives students a lot of trouble. So if you get this correct, you're halfway home. Okay, first we're going to draw a sample. You might hear it described as you're going to conduct so many trials. And when we talk about a sample, we're going to use the variable lowercase n. Now, without replacement, if we draw a marble out of a bag, for example, we are not going to put it back in the bag, right? So after we pull it out, we keep it out. From a population of capital N makes sense, population big, N big. Sample is smaller than a population, it's a subset, so lowercase n, right? Now, this is another place where students start to have problems because there are just simply more variables. First, we talk about variables that relate to the population. Capital S is the items in the population that could be defined as successes. So in other words, if you had a bag of 20 marbles and 10 of those marbles were red, and as you draw, you're trying to draw red marbles, well then you have 10 possible successes in the bag. So you are looking for successes. Now this hopefully makes sense. Capital N minus capital S is the failures in the population, right? If we start out with the whole population and we subtract off the successes that are out there, then we're left with only the failures. Now, in the sample, we also have variables. We've already said that lowercase n indicates the number of trials or the number in the sample, and lowercase x are the items that could be classified as successes in the sample. So, for example, if we continue talking about our 20 marbles in a bag, 10 of them are red. Well, if we're only drawing 2 and we want those 2 marbles to both be red, then there are 2 successes in the sample. Okay, so it's how many we want in our sample. We're going to do an example though, so hang in. Now, this is the formula that you might see in your book, and there are different ways to write this formula. But you can see that there's a need to calculate several combinations, 3 different combinations. Now, the math for a combination hopefully is not too hard, but there are a lot of steps. So it's just important not to get lost along the way. Okay, you may feel like this as you look at that formula. You just simply need to take a step-by-step approach, and I'm going to help you do that. Okay? So here we go. The step-by-step approach for calculating a hypergeometric distribution starts with defining the variables. Again, if you can get this part, you're halfway there. Now, I've already talked about the first 4 variables. I just clean up the math a little bit, and rather than in the midst of another calculation stopping to say population minus successes, I'm going to go ahead and calculate that at this particular point, and I assign it the variable names FP for the failure population and FS for the failure of this in the sample. Okay, and again we're just taking the total population minus the successes in the population, or the sample minus the successes in the sample. Now the real action happens in what I define as step 2, and you'll see that step 2 has parts A, B, and C, and we're just breaking down those combinations. First, we'll deal with the success combination, which takes the total number of successes in the population, factorial, divided by the number of successes in the sample, factorial, and then you can see that's multiplied by, success minus success in the sample, factorial. Okay? So I'm going to call that success. Now, part B of step 2 is the failure combination. And so you can see, FP, where we've gone ahead and subtracted off our successes from the population. And now we just simply compute the factorial and conduct this calculation. And part C of this step is the population combination. Now I realize it's cut off my screen just a little bit, and I apologize for that, but it follows the same format. We're always dealing with the population values at the top and then dividing by the sample factorial, and down here it's lowercase n factorial, times, again, the population component minus the sample component factorial. These things start to pop out at you if you can break it down into these pieces. Alright, once we've done all this combination math, and most of the time your calculator can make that very easy for you, now we just have to take those resulting values and multiply across the top here success times failure divided by population. Okay? So let's do an example. Drawing cards. Now, I realize that not everybody's familiar with the deck of cards. 52 decks in a card, 52 cards in a deck. Okay, the deck is divided into 4 suits, and each of the suits has 13 cards, and so 2 of the suits are red, 2 of the suits are black. Alright, suppose we randomly select 5 cards from our ordinary deck, which is 52 cards, without replacement. What is the probability of getting 2 red cards? And now remember, there's 13 hearts, 13 diamonds. Those are the red ones. Okay? Well, the first thing we need to do is to define our variables. Right? So let's do that. Bring these in. First, we can say that capital N is equal to 52 because there's 52 cards in a deck. Next, we could say there are 5 trials or 5 cards in our sample because that was part of the problem. Now, sometimes you will see R used as the variable for success, and I apologize here, my slide's not up to date. We're using capital S. So how many successes are there in the population? Well, we're trying to draw red cards, and there are 26. Half the deck has red cards. 13 hearts, 13 diamonds. Now, as we draw, we're hoping to get 2 red cards. So in our sample, X is going to be equal to 2. Now we can go ahead and calculate what I call the failure population, and then the failures in the sample, because that'll just help us out a little bit. I'm going to continue on, and remember we said first we calculate the success combination, and you can see where I've simply substituted in the numbers. You can do the math, and you should come up with 325. Now I like to kind of keep a running list, or have those variables listed on my page. I'm going to continue on with the failure combination, and you can see that I would come up with 2600, and again I'm just substituting in my values and doing the math. And finally my population combination, and you can see this is a fairly big number, but that's okay because in the end all I have to do, now that I have those 3 values, is plug and chug, and I should come up with 0.3251, or basically a 32.5%. Okay? So that's how you go through the hypergeometric distribution formula. And I hope this step-by-step approach has helped you to better understand.